Today we have the Dr. Robertson. He's joining us for this interview. Dr. Peter Robertson brings more than 40 years of experience as an educator, researcher, consultant, and practitioner specializing in the areas of in-situ testing and site investigation, earthquake design of geotechnical structures, and soil liquefaction. He is the co-author of the primary reference book on comp penetration testing, or the CPT. He has also authored and co-authored over 250 publications, as well as a popular CPT guide that is freely available on several websites. Welcome, Dr. Robertson. We're really grateful for you to join us.
You're welcome. I'm pleased to be here.
Great. First of all, this is a really interesting question that we, and I think everyone on the world will try to or wants to know from you. What was the reason for you to study civil engineering, and why did you choose to specialize in geotechnical engineering above all the specialties?
Okay. Well, I should probably give you a little bit of background. So I grew up in England. I came from a relatively poor working class family. No one had ever gone to university in my family or extended family. And when I was about 11, I got into swimming. And that sort of really helped me become a lot more focused. So doing competitive swimming, I started to do much better at school. So I started to do well at around 15 or 16 at school, and then eventually transferred over to a school that enabled me to then take the exams to go to university. But since no one in my family had ever gone to university, I didn't really know what I wanted to do, other than the fact that I was primarily studying math and science. So sort of leaning towards an engineering type career. But I became quite interested to become an airline pilot for a while. Oh. And so I spoke to pilots, several of them, and they said, well, you know, we recommend that you should get a degree, because if you become an airline pilot, you know, you have to take annual medical tests every year. And, you know, there's always a possibility you may have to drop out. And so you need to have a career to fall back on. So then I thought, okay, I'll go to university and take engineering as my backup plan. And so I chose civil engineering because it was a fairly general area of engineering. So I thought, well, that seems a reasonable engineering degree. So I went to university. I went to Nottingham University. And part of the reason for choosing Nottingham is they had a university air squadron. And so the Air Force in Britain has a number of sort of reserve Air Force squadrons linked to universities where you can join and they'll teach you to fly. You're not a full-time member of the Air Force, you're just a reserve member. But in return, they'll teach you to fly. And so I applied and was able to get in. And so I learned to fly. And I reasonably enjoyed it, but I realized, I'm not sure I really like this, especially when the weather's not very good. It seems a little stressful. But one thing I did notice is that when I was flying, I enjoyed looking down at the landforms. I would like to look down and look at the different landforms as you're flying along. And so that was my early indication that I had an interest in geology and geography. And so then I thought, okay, I'll finish my civil engineering degree, which I did. And then I got a job in London with a large civil engineering consultant. Actually, it was Sir William Halcrow and Partners. And I was assigned into their bridge department to do structural design. And after about a week, I said, this is terrible. I hate this. Structural engineering is terrible. I can't do this. So I actually got out the application forms to apply to be a pilot again. But at that time, there was actually an excess number of pilots. And so they weren't taking any new pilots in for training. So I said, okay, I'll stick with engineering for a while. And after a few months, again, I was still unhappy doing structural engineering, but there were a group of people in the office from one corner of the office. And occasionally they would leave the office. And so eventually I asked somebody and said, so what do those people over there do? And they said, oh, they're the geotechnical engineers. So I went over and spoke to them and said, so what exactly do you guys do? And they said, well, you know, we do site investigation and we have to go and visit the site. And I thought, wow, that sounds a lot more interesting to actually get out of the office and go visit the site. And so I inquired more, and the more I inquired, the more I thought geotechnical engineering sounds a lot more interesting than structural engineering. And so in inquiring, I also found out that the general consensus was it was a good idea to get a master's degree because geotechnical engineering was more specialized, and the amount of geotechnical that you got at the undergrad level was really not sufficient. And at about that same time, I was deciding that it was maybe a good idea for me to move to another country. I was not that happy with England. England at that time was very much a class system, and I had come from a working class family, and so it became very clear that, well, the successful people in companies like Halcro were generally from private schools and certain universities, and I had not come from that background. And so I thought, no, I think I want to leave England and move to another country. And so I looked at various countries as my option, and sort of places like Australia and New Zealand were a long way away. And so Canada and America were more attractive. Canada was part of the Commonwealth and sort of more European in its lifestyle. So I thought, no, I think I'll move to Canada. And so I applied to go to graduate school in geotechnical engineering in Canada. And the place I was most interested in was Vancouver because it was on the West Coast and the weather was not quite as cold. And so it seemed like a very attractive city to move to. And interestingly enough, the University of British Columbia were the first university to reply and offer me a position to do a master's degree. So I went to Vancouver and I did my master's degree at the University of British Columbia. And I did a research master's, which meant I got a little bit of funding. And my first impression of Canada was I thought this is a great place because as a student being funded to do research, I was better off than when I was working in London. And I thought, this is great. I like Vancouver. And so I did my master's degree, and it was actually with Professor Campanella. And in those days, he was doing laboratory research. So my master's degree was in laboratory research, actually on the creeper effects of sensitive clay. And so after I got my master's degree, I got a job with Golder Associates in Vancouver. And I was assigned to their mine tailings group. And so I worked in mine tailings for about 3 years. And after about 3 years, I realized that I enjoyed geotechnical engineering, but I realized that I was beginning to want to do more diversity in the sort of projects that I worked on. And so I asked Golder if I could move to a different group. But of course, by then they were thinking, well, you know, you're getting pretty good at tailings now, and we'd prefer to keep you in tailings. And so I looked a little bit further afield, and through a close friend, I found out that there was a position available at Fugro in Hong Kong, that Fugro had a small consulting office in Hong Kong, and they were looking for someone to fill a vacancy there. And so I applied. And since I was living in Vancouver, Fugro didn't have an office in Canada at that time. The nearest office was actually in Long Beach, in Long Beach, California. And so I came down to California for my interview. And in fact, the interview was literally only about 10 miles north of where I currently live. So I visited California and I thought, boy, California is a nice place. So they gave me the job. And so then I went off to Hong Kong. And when I arrived in Hong Kong, I was 27 years of age. I had a master's degree and 3 years experience. And the office was relatively small, only about 5 engineers. It had a guy from England who was the manager of the office, and then the rest were local Hong Kong Chinese. And so I was the other English person. And when I arrived, they said, oh, by the way, you're actually chief engineer, because you're the most senior engineer, so you're chief engineer. And so I was 27, I was chief engineer of a small office, but Hong Kong was booming at that time with lots of work. And so in the 3 years I was there, we grew from 5 people to 55 people. So we expanded very rapidly. So my experience grew very quickly, from managing a small number of projects at any one time to suddenly managing lots of projects simultaneously, and projects that varied from major slope stability projects, big rock excavations, to deep excavations, to deep foundations. So huge variety of work, which was exactly what I needed. Having worked on mine tailings, which tend to be larger projects that go on for a long time, I spent 3 years working on hundreds of projects that moved very quickly.
Yes.
And because Hong Kong was booming, it meant that the projects I worked on were being constructed. So you would work on a project, and a few months later, they would start building it. And so you would see your work being done. So if you designed an excavation, within 6 months, they were digging a large excavation. And so you got to see the material that you thought was there, and the same for slope stability. So it was tremendous experience. But while I was there, although I got tremendous experience and I enjoyed what I was doing, 2 things were obvious. One was that Hong Kong has a rather limited geology. It's mostly residual soils, because it's a small area. And secondly, the government had established a geotechnical control office. So everything you did had to be checked by the control office. And that tended to limit innovation. When you wanted to try new things, they wouldn't let you because they were being very conservative. And so it sort of restricted innovation. And then the third thing was that I noticed that although I was gaining a lot of experience, I realized that there was still a lot that I didn't fully understand, that I needed to learn a little bit more. And then I also realized that a lot of the people around me didn't understand either. And so I thought, no, I need to go back and actually do a PhD. I need to understand this a little bit more. And so I looked at various places to do a PhD, and I decided that based on that experience, that the area that I thought needed most work was site characterization. Because in all of the projects I'd worked on, I'd always observed that the site investigation seemed very primitive. You'd go out, and generally it was a mud rotary drill rig, and you would do standard penetration tests, and you would take some samples. And I was realizing that there's got to be a better way to do this. This does not seem a very smart way to do this. And although I was working for Fugro, it was a small consulting office, and so we had no CPT, but I was aware that Fugro were doing CPT, particularly offshore. And so I was aware that CPT existed. And so when I contacted various universities, when I contacted Professor Campanella, he actually said that he had realized the same thing, that he had realized that he wanted to move his laboratory into the field. So he had extensive experience in high quality laboratory testing. So he was building a truck to basically take experiments into the field and do things like CPT and other tests. And that the truck was almost complete and ready for research at about the time that I was ready to go back. So it was perfect timing. Yeah. So I went back to the University of British Columbia. The truck had just been finished. And there was another graduate student, a master's student, and I was a PhD student. And so I did research on in situ testing. But again, with my experience, I didn't just want to do research on in situ testing. I wanted it to have some application. And since the experience I had showed that you could get reasonably good samples of clay, but you couldn't get good samples of sand or sandy soils. And so I realized the most challenging application was in situ testing applied to sands. And since sands are generally quite strong, the biggest application was liquefaction of sands, because that's when sands can suddenly change their behavior a lot. And so my research topic was in situ testing as it applies to liquefaction. So that was the topic I chose to do, which turned out to be very timely and very fruitful. So that was the history of how I got into geotechnical engineering. Not because it was some master plan, but it evolved over time through a work experience and then talking to people and deciding, what were the sorts of things I enjoyed doing.
Yeah.
And that's where the landforms came back, because in doing graduate work, you took courses on geology and geomorphology and looked at things like air photo interpretation. And that's when I realized, I think now I know why I enjoyed looking down at the landforms. I was always fascinated by what shaped the landforms and why they were the way they were.
That's a really great story, Dr. Robertson.
So it's a long answer to a short question.
Thank you for sharing that with us. That really, I think, that really answered the next question. That is, why from all the available tests did you focus a great part of your career on the compenetration test? What is the story behind it?
Well, that's a logical question to follow on from that story, because when I started to research in situ testing, so we had a truck, we had a variety of equipment. So we looked at CPT, and fortunately, Professor Marchetti was in Florida at the time, and he traveled around North America, and he came to visit the University of British Columbia. And with him, he bought his new device, the flat plate dilatometer. So we looked at the CPT, the dilatometer, of course, the standard penetration test. We looked at the pressure meter. We looked at the field vane. We also looked at the screw plate, as well as geophysical techniques. So we looked at a full range. And very quickly, I realized that the CPT showed the most promise, because it was fast, it was continuous, it had multiple measurements. And also during that research, we had heard that Fugro in Long Beach were doing CPT testing, and they had added a geophone to measure shear wave velocity. So we traveled down, so I traveled back to California, and we visited Fugro, although at that time, the California office had converted over to a company called EarthTech. And we visited with them, and they showed us that, yes, they had put a geophone inside a sort of a dummy cone so that they could measure shear wave velocity. So Professor Campanella and I went back and said, well, so why don't we put a geophone inside a full cone so we could measure tip, friction, water pressure, and shear wave velocity all with one device, which we did, and it worked extremely well. And that's when we realized, wow, this is a fantastic test. It's fast, it's continuous. We take all these measurements, tip, friction, pore pressure. We measure shear wave velocity. We can do dissipation tests. It's like this is likely the most promising test for the future. And so that was why we began to focus more and more attention on it.
Great.
Yeah.
And I think it's turned out to be the right decision.
Completely, I agree with you.
It's somewhat frustrating that industry around the world has been slow to fully grasp that. But I think now, 40 years later, industry has embraced it, and you do see that the CPT is beginning to be used in many places in the world. It obviously depends on the geology.
Yeah.
You know, there are places where you have hard rock close to the ground surface and the CPT is not suitable. But in general, if you look around the world, most of the densely populated areas tend to live in coastal regions or in rivers or in valleys, etc. So people tend to live in flatter areas where the ground is generally softer. And so CPT has generally good application where most people live. And so if you look at places around the world where CPT is used, it's generally a combination of suitable geology and large population. So here in California, for example, there's two main population bases. There's the San Francisco Bay Area, which is basically soft clay in the Bay Area. And then here in Los Angeles, the other big area, it's a relatively large, flat, alluvial area where, again, it's generally very suitable to CPT. And again, when you look around the world, of course, in the Netherlands and Holland, it's soft ground. And so CPT is used extensively there.
Yeah.
Oh, great. Yeah. And if you could choose one of your projects to be the one to represent the most challenging, which one is it? Could you please tell us?
Did you say which project has been the most challenging?
Yeah.
Yes.
Yeah. Well, in recent years, ironically, I've sort of gone back and I'm doing quite a lot of work in the mine tailings area. And so almost 2 years ago, there was that large tailings dam failure in Brazil.
No.
And I was asked to chair the expert panel to investigate the failure. And so that was a challenging project. It was quite large and very detailed to try and determine the cause of that failure. And in recent years, I've been working quite a bit in the mine tailings area, and they certainly have challenging projects. Many of these tailings dams now are very large. They cover a very wide area. They retain very large volumes of mine tailings. And of course, those two failures in Brazil highlighted the severe consequence if they should fail. And so there's been several quite large mine tailings jobs that have been very challenging.
Yeah, so the most challenging for you would be the one of Fundão, the failure of Fundão, or?
I was involved in the one that's often referred to as Brumadinho. It was located close to Brumadinho.
Yes, yes.
Okay. Fundão was 2015, Brumadinho was 2019.
Oh, yeah, okay, yeah, you're right. Wow, it's been...
but both were liquefaction, and so of course...
Yeah, both were the same thing.
The history is that it was liquefaction of sort of sandy type materials, and of which the CPT was the primary testing device. Mm-hmm. And so, historically, that work I'd done in my PhD was very applicable. Yeah,
completely. And that kind of drives us to this next question. To put yourself on a bit of context, the compenetration testing, or the CPT, arrived to Peru relatively a few years ago, mm-hmm. and it wasn't popular at all. Like this wasn't popular, wasn't known for many engineers, made the test more expensive, which also made it even less popular amongst the engineers. So, but also little by little, because all of these failures, because the interest in Peru of the mining and the tailings and facilities, mm-hmm. it increased the amount of CPT used in the projects, and we've been seeing some CPT use also in the buildings area. We would like for you to tell us the story, like kind of like you have already did. From your perspective, did the test had the same rough start in the US or in England? And what can we expect from Peru to the future?
Yeah, well, that's a good question, because in North America in general, so back in the in the 1980s when we were really writing a lot of papers about the CPT. When I visited companies, you would hear the general criticism that, well, you know, the SPT's been around a long time. It's very reliable. It's cheap. You know, why would we bother to do the CPT? It looks like it's much more expensive, and I'm not sure I can believe it. So there was a lot of skepticism, and I think a lot of it is to do with the training of how people become engineers. You know, often people go to university, they get their education, and then they start work. And, you know, after about 20 years, you know, their education seems a long way away. And now they're basing mostly off their experience, and often their limited experience within their local geology and their local environment. And so a lot of older engineers were very comfortable with the SPT because they had used it for maybe 20 or 30 years, and they were comfortable with the numbers, even though the test is not that reliable. You know, they were just generally comfortable with the numbers. And when someone comes along and says, look, we've got this new test, and I get all these squiggly lines on a chart, and their first reaction is, I don't think I don't understand this. I don't trust it. I don't understand it. I don't know anything about it, so I'm not going to do it. And so what you see is that, of course, those older engineers were generally the senior engineers in their companies. And quite often, if they didn't trust it, then the company wasn't going to do it. Okay. But I think what you've seen is that over years, younger engineers who have now been taught about CPT at university, so they've had a course, usually at the graduate level, but increasingly now at the undergrad, it's being introduced. So that these younger students are coming out and they're aware of the CPT, and they would join the company and say, well, why don't we try the CPT? And of course, the older guy would say, no, we don't trust that. I'm not going to do it. But now those younger engineers are becoming more senior, and they're a little bit more adventuresome. And of course, also the cost has come down. But also in the publications, you know, more and more publications are showing CPT data. When case histories of failures occur, it's nearly all CPT data that's being presented. So the industry is being forced to sort of look at this test to say, look, well, this is what researchers are doing whenever a failure occurs. This seems to be the state of the art, the way we should be doing things. And so it slowly comes in. And then, of course, you know, with lots of publications, I produced that CPT guide that was freely available. And then I've done webinars, all ways to try and educate people to say, you know, this is not as complicated as it seems. And then also trying to educate people that superficially they would think, well, the CPT is more expensive. But then you would educate them to say that, yes, but keep in mind, it's much faster, and it collects much more data. And so if you think of the cost of an SPT blow count, so if you go out and drill a hole, and let's say during the day you do 20 CPTs, so that blow count is actually very expensive. Whereas if you go out with the CPT, and in one day you could do 5 CPTs, each CPT collecting 1,000 data points. So you have 5,000 data points. Each one of those data points is in fact remarkably inexpensive. And so educating people, it's like it's not as expensive as you think it is. In fact, it is in fact much cheaper. But what you tend to find is that in developing countries where labor cost is still quite low, then labor intensive testing like the standard drilling and the standard penetration test is still quite attractive because it's quite inexpensive because labor costs are so low. But in developed countries where labor costs are becoming very high, then automation and things like CPT become much cheaper because labor costs are so high. And so you want something that requires less labor and is much faster. And so when you look around the world, in countries where labor costs are very low, the CPT has been slow to become adopted. But as those countries develop and labor costs slowly climb, then the switch over to CPT becomes more rapid.
But this is kind of an adjacent question, just a little one. How can we help to the older senior engineers to understand that the CPT is actually a better data, or gives actually better data info than the SPT, for example?
Yeah.
For example, maybe a comparison between the a CPT graph and an SPT graph that kind of give the same on maybe the point resistance or the tip resistance, but also gives you a lot more, like friction, like you just said.
Well, when we first started to do research in in-situ testing, one of the first publications we wrote was a small paper in the ASCE journal on comparing CPT with SPT. So it was a small paper called CPT-SPT correlations. And so a very simple paper like that ended up becoming very useful, because a lot of older engineers who were comfortable with SPT blow counts, when you then say, well, I've got a CPT cone resistance of 20 megapascals, the engineer would say, well, I don't know what that means. I don't know, is 20 megapascals good or bad? And so if you could convert it to a blow count and say, well, this is a blow count of about 40, and they would go, oh, well, that's good. So, okay, if you can convert it over to blow count, that would be helpful. And so in the early days, it was very common to take the cone profile and also produce an equivalent SPT profile. Yeah. And then the engineers would look at that profile and say, oh, I quite like the way that it's continuous. So I get all these blow counts in a continuous way. And so now I can see all the layering that I couldn't see from the drilling and the actual blow counts. Yeah. And when they overlaid the actual blow counts, they could see that they agreed reasonably well, except that the actual blow counts were missing all of the detail. Yeah. And so that simple comparison became one of the most popular publications in the early days, because it helped people transition from one to the other. And in more recent years, I got involved in software development. Again, quite by chance. There was a man in Greece who had started a small software company, Geoweek, and he sent me an email about 10 years ago and said that he had programmed my liquefaction method into one of his programs, and could I take a look at it to see if he'd done it correctly? So I did. I looked at it, and we interacted, and I made suggestions about how he could present the results maybe in a more clear way. And then he sent me an email and said, could I suggest another program that he could possibly write? And I said, well, actually, that's a good question, because there's a real need for good quality CPT interpretation software that's inexpensive. Yeah. And so Greg suggested that we could offer a small amount of money to help him write the program. And we didn't want anything in return. We'd say, look, no, we don't want any sort of share of the sale. And I'll help you develop the software. We just want to see software like this available. Yeah. And so I worked with John Ioannidis in Greece, and his company is Geoweek. And we wrote a little program called CPTite. That's how you pronounce the name of the program. It's called CPTite. It's sort of a play on words that petite is French for small. So it's a small CPT program. Mm-hmm. And so that became very useful, because first of all, it forced us to think about how would you actually do it? It's easy to write a paper and say, this is how you do it. It's another thing to actually write a software program that will do it for you. Okay. So that became very useful. And then that in itself has become an extremely useful education tool, where you can show people how quickly you can interpret the data and how much information you can get out. And so that sort of progresses on from that simple conversion to SPT. And of course, one of the plots in there is an equivalent SPT blow count, but there are so many other plots in there. Yeah. and they're all in color, and it's easy to use. And so people then, when you show them how quickly you can load the data in and how quickly you can get results, most people are very impressed in the sense of saying, wow, that was really quick. You did that very quickly, and yet we've got all this information laid out. It's incredible.
Yeah.
So it's become a very useful teaching tool, as well as, of course, an application tool for thousands of people. So I think that's what happens. You start on something very basic, and then you begin to build with the software.
Yes, completely agree with you.
And a little bit of background, when I visited Lima some years ago, I realized why CPT hadn't caught on in Lima when I saw the large exposures of gravel.
Well, yeah.
you drive along that coast road and you see these vertical cuts of dense gravel, and think, I'm assuming they don't do a lot of CPT in Lima.
Yeah, it's kind of rough to do a lot of some testing in this particular gravel.
But Peru does have a lot of mines, and you have a lot of tailings dams, and that's clearly a good starting point.
Yeah,
because they're high risk, they're high dollar value, and so they can afford to get the CPT out there and get lots of data, and then progressively bring it into sort of more local projects with less expensive equipment.
Thank you.
A little bit of background, of course, one of the companies in Peru is Contech.
Yes, of course.
And when I was at the University of British Columbia, when I finished my PhD, two things happened. One is that, when I was in Hong Kong, I was married, and we were expecting a baby. So when I went back to do my PhD, we actually had a baby. So if someone had told me when I did my master's degree and said to me that, well, in 6 years' time, you're going to come back and do a PhD, you'll be married and you'll have a baby, I would have said, you're crazy. There's no way I'm going to do that. But anyway, so I went back to do a PhD, and we had a baby. But my wife died, she died of cancer. And that was the reason why I decided to move into academia, because I was a single parent with a young child. And the thought of going back into industry with all of its associated travel became very difficult. And so Professor Campanella had suggested that, well, why don't I could apply for a postdoctoral position that would allow me to stay at the university, while I potentially look for an academic position. And so that was actually the decision that moved me into academia, was that background. Now, I've forgotten exactly why I digressed onto that little bit of storyline about why I moved that way. Can you remind me what triggered us to go down that path?
Well, we were talking about the case in Peru.
Yeah, that's right. I was talking about Contech. Yes. So I got this position at the University of British Columbia, and when I got the position, Professor Campanella went off on sabbatical, so I had to take his teaching load. And so that first year, I taught a graduate course on site investigation, and I had a number of people take that graduate course. Some of them were sort of mature students who had worked in industry but wanted to take a master's degree. And one of them was David Weller. And David had worked in industry, and he took the course. And after the course, he came to me and said that he was really impressed with the stuff on CPT. And why was it that nobody was offering CPT in Canada? And I said, well, it's a bit of the catch-22 is that nobody's offering CPT because nobody's asking for it, and nobody's asking for it because nobody's offering it. And so, there is a need for a company. And so he said, well, I'm going to start a company to offer CPT. And he came back a few weeks later and said, look, I've got this printout from one of the manufacturers. What's the bare minimum of equipment I need to buy? So we went through the list and ticked off the bare minimum. And then a few weeks later, he came back and said, I've started a company and I'm going to call it Contech. So that's how ConeTech got started.
Oh, that's a really nice story. I'm going to refer this video to our ConeTech friends that have worked there, and we are currently working there here.
Yeah.
Thank you.
So David started very small. He asked permission if he could continue working for the consulting company he was, and then do CPT as a little bit of a side business. So he did that for a short period of time, and then realized, no, he had to leave and do it full time. But it started off where he had the very basic cone equipment, and he would push CPT off the back of other people's drill rigs. So they would contact a driller, and then he would go out and push the CPT off the drill rig. And then it grew from there. Yeah. And now they have offices in quite a number of countries, primarily North and South America, but they have an office now in Australia. Yeah. And they're one of the biggest CPT land-based contractors in the world.
Yeah, yeah, completely.
Of course. Now, what question? What is the thing that you most enjoy about being a geotechnical engineer?
Well, go back to that original story about how I got into geotechnical engineering, is that those people would leave the office and they went outside. And I think that's one of the enjoyable elements about it. And the other element is structural engineering is very codified. You're dealing with, concrete or steel, of which we know a great deal about. Whereas in geotechnical engineering, we're dealing with natural ground, of which there's lots of uncertainty. And so that combination of needing to go out in the field to actually see it and test it, and then the uncertainty, the fact that it's often a naturally deposited material with often large variability and large uncertainty. And so the challenges of dealing with all of that uncertainty is very rewarding. It's not suitable to all personalities. Some of my friends at graduate school were structural engineers, and they really enjoyed what they did. But I find that the uncertainty creates one of the big challenges for geotechnical engineering, which makes each project a little different.
Yeah.
Right.
And it's also why the CPT becomes very popular, because you're dealing with uncertainty and variability, and the CPT provides you lots of data. You can push 10 or 20 CPTs relatively quickly, relatively cost effectively. You get thousands of data points. So now with CPT data, you're beginning to see statistical variations come in more, that you've got enough information that statistics becomes a valid option. In the old days when you went out and you drilled a bunch of boreholes and you had a bunch of SPT blow counts, you never really had enough data for it to be statistically meaningful. Yeah. But now we have thousands of data points that we actually can do statistics and start to quantify some of the variability, which moves us in the direction of a more probabilistic design. And you can see that coming, that for large projects, risk assessments are being done in a more probabilistic manner because we now have enough data. And when I first got into liquefaction, back in the 1980s, there was very little data that would link CPT to case histories. Now we have literally tens of thousands of case histories, particularly after the earthquakes in Christchurch in New Zealand in around 2010 and 2011. The government decided that they had to investigate so many sites that the CPT would be the preferred way to do it. So now Christchurch has over 30,000 CPTs in a public database linked to the performance of 4 earthquakes. Whoa. And so now we actually have a massive database. And so I think we're entering an interesting period where we may actually be able to start using big data. So actually, instead of interpreting CPT data by saying, well, we've got theories and empirical correlations, we actually have the possibility to take your CPT and go search the database for a similar profile.
Yeah.
And then for the database to say, we found one or two similar profiles, and this is how they performed. Those sites performed this way. So there's no theory, there's no empirical, it's simply big data saying, we've got this massive database that enables us to get some insight into the performance of the site. So I think that's the next era that we're entering.
This is more of more focused on your experience as a professor and for the students or that would like to actually know, and we would like for you to transmit that. How can you enhance the critical judgment or the engineering judgment in the students? Like anyone can replace a formula, but not everyone is capable of assessing the situation they have in their hands. It's like the observational method that from Professor Peck.
Yeah. Well, there's two things, and probably they in a way link back to Peck. One is, I've often said to young engineers and students, is use your powers of observation. It's also linked to the sort of the general comment about don't drift through life. You know, try to make conscious decisions about what you want to do. And when I was a young engineer, I used to try and make sort of 3 and 5 year plans about, well, what would I like to be doing in the next 3 to 5 years, and actually make a conscious decision. You know, so when I left Golder and moved to Hong Kong, it was a conscious decision that I wanted to get different experience. So, you know, make conscious decisions in your career and use your powers of observation. When I lived in Hong Kong, there was lots of construction going on everywhere. And so everywhere I walked, you would pass a construction site and I would stop and have a look. So if there was a deep excavation, I would stop and have a look to see what they were doing, why they were doing it. And I find I constantly do that, is use your powers of observation. So even in the field, when you're in the field and you're doing a site investigation, you know, observe what's happening. You know, I can remember, you know, sitting on a drill rig and you'd be watching the drilling and something unusual would happen. And you would ask the driller and say, well, what was that? What happened then? I didn't understand. And then you would interact with the driller and the driller would explain that he thought it was this. And so, you know, ask questions, use your powers of observations to gain a greater insight. So that in a way links to Peck and the observational approach.
Yeah.
So slightly different, but use your powers of observation. And then the second one is Peck, in one of the videos that he gave, talked about a sense of magnitude, a sense of understanding. So, you know, when you're working on projects, you need to have a sense of what the answer is likely to be. And so early on in a career is develop that sense of magnitude of what things should be. Peck, you know, gave an example of, he would ask students and said, well, how long is a typical suspension bridge? Which is a strange question, but he wanted them to have a sense of, well, roughly how big is a suspension bridge? You know, it's obviously not 100 meters, and it's obviously not 100 kilometers. You know, it's sort of, well, on average, it's about 1 kilometer long. And so you have a sense of what the number should be. And when you're doing, and particularly now with computers, where computers will do calculations for you, you need to have a sense of what the answer is likely to be. Yeah. And so using often very basic principles that you've learned to get a sense of, well, what do I think the answer is going to be? You know, slope stability, you know, simple things is, if the friction angle is around 30 degrees and the slope is, you know, a 20-degree slope, you know, what do you think the factor of safety is going to be? You know, it's going to be roughly the ratio of the tangents, you know, the tangent of the friction angle over the tangent of the slope angle. It's roughly that order of magnitude. as long as there's no high water table. And so having a real sense of the numbers is very important. And that ties into observational method, is, be observant, when you see everyday things, take a note of what are the typical numbers. I remember a story, when I was working in Hong Kong, one small project, there was an existing old retaining wall that needed to be evaluated. And the engineer came to me and said, I think we should do some direct shear tests on the backfill to get the friction angle. And I said to him, why do you want to do that? And he said, well, I need the friction angle to check the stability. And my answer was, well, what do you think it is? And he looked at me as like, that's a strange question. I said, well, take a guess. What do you think the friction angle is? And of course, he eventually said, well, probably around 30 degrees. And I said, there you go. So why do you need to do the direct shear test? And he said, well, I need to know the answer correctly. And I said, but you know that it's standing there. It's an existing retaining wall. So why don't you just back analyze the existing retaining wall? You know it's stable. Well, you know it hasn't fallen over yet. So you know it's got a factor of safety of at least 1. So why not back analyze to get the friction angle? And of course, when he did that, he came back and said, oh, it's like 38 degrees. I said, well, there you go. You don't need to do the direct shear test. and so it's that thought process of going through, the observation of what do you think it is and what's a reasonable value.
Yes, that's right. I totally agree with you. And it's a question. Well, the next question is a little bit more personal. From your personal point of view, what does geotech mean for you?
Oh gosh. I think overall, at least from a personal perspective, I've enjoyed the career I've had. I've enjoyed the variety it's brought, because actually when you look back at it, so I worked in consulting, then I went into academia, and now in California, I'm a technical advisor to a contractor. So I've done consulting, academia, and contracting. So I've really enjoyed the wide variety of work that it's given me. And it's been rewarding and generally quite successful.
Great answer. Thank you.
I think, when you said, what's it been personally to you? I think advice for young engineers is that you want to work hard so that you can succeed at what you want to do, but at the same time, you want to have work-life balance.
Yeah.
And it's important to have work-life balance. And I think, I mentioned about my wife dying, and, a major event like that changes your perspective a little bit. And so certainly for me, that was one of the biggest events in my life that changes the way you think about things. And so work-life balance becomes quite important. And I know throughout my career, I've worked with lots of people that, in my perspective, devoted too much time to their work. They would work very long hours at the cost of family time. And I think the lesson is, no, you only have one life, and you really want to get a balance. And everybody chooses to make that balance slightly differently. But again, it's important that you make a conscious decision about what is the appropriate work-life balance for you. And if I give a little bit of philosophical comment, is that over the years, I've realized that for a happy life, in a sense, you need 4 things in your life. One of them is you need to be happy with who you are as an individual. Mm-hmm. That's the number one. You have to be happy with who you are. And then secondly, you have to love what you do. You have to love the relationship you're in, and you have to love where you live. And in hindsight, I now live in Southern California. And so in hindsight, I realized, well, assuming you're comfortable with who you are and you love who you are. So out of the other three, I realized, having traveled and lived in many places in the world, I would pick the location you want to live first, because you'll always find something you enjoy doing there, and you'll always find a relationship you'll be happy in. But choose the place you want to live in first. because if you live in a crummy place, you're happily married, you love the job you do, but you're living in a crummy place. That living in a crummy place is always going to bug you. So move to a place you're going to be happier to.
That's completely.
And that varies for everybody. Some people like living in big cities, some people like living in the country, and so on. It depends on you as an individual. But make a conscious decision.
What you just said actually drives us to one of our last questions. That would be, which abilities do you seek or do you wish to encounter on a student or on a future geotechnical engineer or engineer in general?
Yeah, I think an inquisitive nature. Another observation I've often made is that the person who is the top student doesn't necessarily go on and have a very successful career, because the very top students often think a little bit differently than everybody else, and often have difficulty communicating with everybody else because they think on a different plane than most other people do. So it's not always a good idea to be the absolute top student. It's communication skills are very important. So somebody who's inquisitive and has good communication skills is a good thing. And in graduate school, if you're going to do experimental work, being inquisitive is a good thing.
Yeah, and for our last question, this would be, which would be your recommendations to the new generation of geotechnical engineers, if you kind of like imagine that you're addressing to them?
Well, I think this geotechnical engineering is a good career. It offers lots of challenges. There's still lots of things that we're learning and doing. I think we will see a lot of progress in the future. I talked about this vastly improved site investigation techniques, and it's all digital data now. So people collecting data in the field, but you're able to look at it in the office almost in real time. As a young engineer, I remember working on projects maybe 1,000 miles away from the office, and it would, you were gone for several weeks, and the project engineer wouldn't get to see the data until you got back to the office. Whereas now you can email the data, it can be looked at in real time. So there's lots of progress, and the volume of data means that, analyzing it in understanding the variability in more detail, there are lots of challenges. So more probabilistic, more risk assessment in the future. Professor Morgenstern, I think, gave a talk where I think the topic of the talk was, we're moving from a period of certainty to a period of uncertainty. And I think what he meant from that was moving from where we think we can calculate a factor of safety very accurately, where in reality, we should be working in probability, where we're dealing with uncertainty.
Yeah, like seismic evaluation, for example.
Yeah. So there's lots of challenges, and it can be a great career if you're suited to it. But it doesn't suit everybody. So one of the early things is, do you think that sort of work is going to suit you?
Well, it suits for me. Thank you. That will be our last question. And we're going to actually cut this small part because we would like you to invite everyone who's watching this video, this interview, to assist to the Congress and to maybe join you on your presentation as well. So whenever you're ready, you can just start the small invitation.
Okay. Well, it's been a pleasure talking to you, and I hope that we're all going to get an opportunity to meet in a virtual sense at your Congress in November. I'll be giving a short talk, and I hope many of you watch the various talks, and hopefully watch and listen to my talk, and hopefully we'll have a chance for some interaction, even though it's in a virtual sense. And hopefully I won't have the plaster on my nose by then.
No,
Thank you.
Okay. That works. Well, thank you so much for your time, Professor Robertson.